All right, welcome everybody. Please take a seat so we can get started. Again, I've selected a couple of problems that we can go through today from the suggestions that you have made. We probably won't have time to cover them all, so I thought it's probably best to just put that to a vote before we start, and then work through those in whichever order you desire. So here's a tweetback question asking for which problems you want to discuss today. I'll quickly scroll through those. Everybody can submit up to 3 votes. So first one, 2022, number 2, image and kernel. That's the one you're just seeing here. Here's one from 2021, number 5, matrix games, so game theory question. Here's one that I think we haven't covered all of those yet, problem 6 from 2022, basis transformation. So this is about matrix representations of linear mappings. Here is a problem from 2020 to 2021 on series convergence and series limits. Here's another game theory question from 2016 this time. And I think not quite the final one. Problem number 9 from 2022. This is one about local minimizers and local maximizers, so curve sketching basically, but without a sketching part. Here's one from 2016 too that probably looks somewhat familiar, but it was still on your list, so I'm listing it here anyway. Taylor series. And that's the final one from 2016, sequence convergence. I'll slowly scroll back, and in the meantime, please submit your votes on this tweetback question here so that we have an order, and then we work our way through that as far as we can get. So I'll give you 1 more minute to submit your vote, and I'll scroll through those once again. I can select 1 minute, so maybe make it 2. So once again, quick overview of the questions that I'd like you to vote on. And let's say 30 more seconds for your vote. And I'll scroll back in the meantime. Okay, so here's the results. So we'll start with 2022, number 2, the first one I just see here. That got the most votes. And then I guess we'll skip to the third one, matrix representation. Pretty much what I was expecting. All right, and then, can I have the number of votes somewhere? Let's see. Same number of votes. All right, well, we'll see if we can manage to do both then. All right, so let's start with that one right away. Image and kernel. So basically what we have here is a linear mapping that is given by a matrix. So f of x is a matrix times the vector x. And I'm asking for the basis and the dimension for the image of f here in A and for the kernel of f in B. That should be pretty much standard fare. There's one catch, however, and that is that vector space U here. So f is not defined on R3, as you would normally expect, but just on a subset. And geometrically, that subset here is defined by one linear equation. So geometrically, that's a plane through the origin, right? So f is defined on a plane in R3, and the codomain is R3 as usual. So how do we deal with that? First, it might be a good idea to find a nicer description for that set U here, right? I mean, you can work with that, but usually it's a good thing to have those domains in an explicit way. And by explicit, I mean I'd like to know a basis so that I can explicitly construct vectors that are in U. So that would be my first step here. I'd like to determine a basis for U first. That's not hard to do. Basically, U is described as the solution space of this system of linear equations, right? So U equals the solution space of x1 plus x2 equals 0. Right? So if you write this in matrix vector form, the matrix would look like this, just one row, 3 columns, because U is a subset of R3. And that's it. This is, of course, already in row echelon form, so not a lot to do here. Just notice this here is a pivot element. So that means those two here, those two variables are free variables. And then we should be able to basically write down a basis for U right away. So U is the following set. X2 and X3 are free. And we just need to solve for X1. And if we solve that for X1, we just get X1 is minus X2. Right, so we have our free variables X3. Doesn't appear anywhere in this X1, so there's a 0 here. X2 is also independent of X3, so there's a 0 here and a 1 here. And we have X2. 0 for the X3 component, 1 for the X2 component, and then for X1 we have this equation here. X1 is minus X2, so we need a minus 1 here. So that's an explicit representation of the set U, or you could also write that as the span of those two vectors, 0, 0, 1, and minus 1, 1, 0. Right, and that, these two are then a basis of U. Okay, any questions up to that point? Yeah. Why is it what? This? This one? This one? That's because of this equation. I'm translating this into matrix vector form. It's one equation, so the matrix will have one row. We have a subset of R3, so we're here, right? The x's have 3 coordinates. So we need 3 columns, and the coefficients are 1, 1, and 0 for the x3 variable that's not in this equation. Right? So that's just a translation into a matrix, right? Of course, you wouldn't have to do that. I mean, just looking at this equation, you can probably already guess correct solutions, so it would be sufficient to just write that down and say, obviously, this is U. All right, so now the first question is, I think, for the image, right? Yeah, the first question is for the image. Remember, f of x is defined in terms of this matrix here, 2, 1, 1, 1, 0, 1, x. And you just get the image if you plug in all vectors in the domain for this x, and then generate all possible images, right? Now, the domain is a vector space, so it's sufficient to plug in a basis, and luckily we have a basis. So we just plug those in, and the result will span the image of f. So the image of f is going to be the span of f of those two basis vectors. Right? And that's why I needed those, or one reason why I needed those. I couldn't just plug in R3, and if I operate directly on the matrix, that kind of assumes I can plug in R3. That's not true. So I need that basis first, and then I can just plug in the basis vectors and compute the values for those. Well, what do I get? I just multiply this here by the matrix. So matrix times 0, 0, 1. That will just yield the last column of the matrix. So that's 1, 0, 1. And then matrix times minus 1, 1, 0. That means I have minus 1 plus 2. That's a 1. Then I have minus 1 plus 1. That's a 0. And I have 0, 1. That's a 1 again. And as you can hopefully see, those two vectors are multiple. They're the same, actually. So it's sufficient to just keep one of those. Right, so generally we reduce that set to something linearly independent, so we get a basis of the image. So this set here now is a basis of the image of f. And thus the dimension of the image of f clearly is 1. Okay, so that's how I would determine the image. Questions on that part before we proceed to the kernel? No? Okay. So next part, part B, determine the basis and dimension of the kernel. If we're doing that, we already have the dimension of the image, and of course we also have a dimension of the domain. It's always a good idea to first compute the dimension using the well-known rank nullity theorem. So even if the dimension was not asked for explicitly, it's still a good idea to have that in mind, just to check whether your solution might or might not be correct. Yeah, and it's not really a lot of work. So the dimension of U, the domain, is equal to the dimension of the image of f plus the dimension of the kernel of f. And well, what do we have here? The dimension of U is clearly 2. You have a basis that has 2 vectors. The dimension of the image is 1. So the dimension of the kernel that we're looking for must also be 1. Right? Dimension of the kernel of f is 1. So we've settled that already without any additional computations, almost. So what that means is all we have to do is we have to find one linearly independent vector in the kernel. And remember, the kernel is the solution set of f of x equals 0, right? So kernel of f is all x in U, where f of x equals 0. Again, the problem here is we have this domain U, so we're only interested in vectors that lie in U, not vectors anywhere else in R3. And there might be more of those, but we just want those in U. Now, let me first present a shortcut here. If you've been paying attention in A, you should be pretty much done by now. Because as you can see, we computed the images of those two basis vectors here, right? And we found out they all map to the same image. F is a linear mapping. So if I subtract those two, if I take the difference, the result would be the zero vector. Well, how do I get those two? Well, it's this and this, or this minus this. And that, of course, I can use to construct a vector in U that has exactly the property I want. So let me just write that down. From A, we already know that f of 1, what was it? F of, what's my basis? 0, 0, 0, 0, 1, sorry. Let's start with that one. 0, 0, 1 is 1, 0, 1. And we know that f of, what was the other one? Minus 1, 1, 0. That is the same vector. And that means f of 0, 0, 1 minus f of minus 1, 1, 0 equals, well, the difference of those two images, and that is obviously the all zeros vector. So as f is linear, that means we know that we can take those together, right? So instead of taking f of that minus f of that, we can take f of that minus that directly. So by linearity, this is the same thing. And that means this vector here is in the kernel. And this vector is, let's see, this is 1 minus 1, 1 is in the kernel. The kernel is one-dimensional, so any non-zero vector will be a basis. And that means we're done. 1 minus 1, 1 is a basis of kernel F as the dimension of that kernel is 1. Okay, so that's the quick way. Let me also quickly comment on an alternative in case you don't see that. Of course, you can also do that in a more elementary way. Pretty much the same idea. What we want is, we want a vector that maps to 0, or we want all the vectors that map to 0, basically. All the vectors in U can be formed by a linear combination of the bases, right? The basis, again, where do we have that? The basis is this one here, 0, 0, 1, and minus 1, 1, 0. So all vectors in U can be written in this way. For coefficients lambda in R, so that's the same thing as the set U. And that means all we have to do is find all lambda 1, lambda 2, such that f of this general element here maps to 0. And of course that amounts to the very same thing. Again, we can just use linearity and say, well, this is the same as lambda 1 f of 0, 0, 1 plus lambda 2 f of minus 1, 1, 0. And this in turn is the same thing as, well, we know those images already, lambda 1, 1, 0, 1 plus lambda 2, 1, 0, 1 is 0, 0, 0. And from that, just determine the set of all lambda 1, lambda 2 that will solve this. Right, and that will give you your kernel. Yes? Sorry, do you have? I didn't get that. What do you mean by the image of the right-hand side? Mm-hmm. You mean this here? Mm-hmm. It depends on what you want. So what I want in this case is all the points that map to 0, right? So the outcome is fixed at 0. That doesn't have to do anything with f. Yeah, we just want all the points on the left that are mapped to this specific point by f. And of course, you can do this for any other specific point that you want. Might be infeasible, but you can still try. And then you don't have to compute a mapping of f, right? If the question asks for find all the points that also map to the same as this point, right? If the question was phrased differently, then you might have to do that, of course, but not in this case. And maybe just a quick reminder here, in this case, it doesn't really matter because f of 0, 0, 0 is always 0, 0, 0 for a linear mapping, right? So no difference here. But of course, it might be different for different right-hand sides. Yeah, you're right there. Yeah. So you're referring to the rule that the image of f is the column space of a matrix. And generally, you're right. What we did there is we argued that the image of f is basically the linear combination of all the columns because we can put in everything from the domain, and the domain is a complete R to the k, right? So we can just use the canonical basis, put that in, and then we get all the columns, and we can take all the linear combinations. That is true if the domain is some R to the k, if it contains the canonical basis, basically. That's not the case here. So the difference is we have a restricted domain. We just have this U here and not R3. Your approach would be correct if you used R3. Okay? Question? That's, so for the kernel, your approach would be to just take this matrix, let's call it A, and solve this system, right? Pretty much the same answer. So this works if we're looking for the kernel over an R to the k, right? Using this matrix approach always assumes the domain is some sufficiently large R to the k, where k is the number of columns of the matrix. That's not the case here. Our domain is smaller. What you could do is you could use this approach, get a kernel for a larger domain, and then intersect that with the domain that we actually have. But you'd have to do this additional step. And pretty much I did that step by first restricting to the domain, but you could also do it the other way around. Where? For lambda 1, lambda 2? Okay. So you determine the correct values for lambda 1, lambda 2, and then you just compute that linear, sorry, not that linear combination. You compute that linear combination. That's the one you want, right? So usually you'll get a solution that says something like lambda 1 is minus lambda 2 or something like that, and lambda 1 is free. So you get a whole bunch of possible combinations. You just plug that in, and then you should get the same result as I have. Give it a try. That shouldn't be hard, hopefully. Question, yeah? How do I know that x2 and x3 are? Are you referring to, where do I have that? This part here. Okay, so what I did here is I translated that into matrix vector form. This is the matrix. And then to solve a system in that form, I usually reformulate that to a row echelon form using Gaussian elimination. Then I have a look at the results, see where my pivot elements are. And all the columns that don't have a pivot correspond to free variables. In this case, there's only one row, so this is my pivot element, my only pivot element, and there's no pivot in the other two columns here, no pivot here, no pivot here, so those correspond to free variables. That's how I do that. Yeah, basic SLE solving. Just the SLE is very simple in that case. Maybe that's confusing. Yes. Where exactly? You mean here? All right, maybe let's solve this anyway. So just to clarify, what I would do here is basically this is a system of linear equations, which 3 equations, right? The first one is lambda 1 plus lambda 2 is 0. The second one is 0 is 0. And the third one is the same as the first one. Right, so I can just solve one. Let's say I solve this for lambda 2 is minus lambda 1. And if I plug that in here and here, of course, that will all be feasible, right? So that's my solution set. And that means I plug that in now. Plug that in for lambda 1, lambda 2 in, let's copy that here. So what I said is all vectors in U look like this. So I can just plug that in here. And what I get is, well, I said I solve for lambda 2, so let's plug in this for lambda 2. And lambda 1 is a free variable. Maybe I should mention that as well. So lambda 1 is free in that case. And I get lambda 1, 0, 0, 1 plus minus lambda 1, minus 1, 1, 0. Right? And well, I could, of course, simplify that a little. That should yield, let's see, lambda 1 minus lambda 1 and lambda 1. And that means the kernel of f would then be lambda 1, 1 minus 1, 1. Where lambda 1 is free, so that's in R. And as you can see, that's the very same thing I had before. Does that answer the question? Don't remember who asked that. Good. Yes. That's fine. So what? So you got the negative. Yeah, of course you can do that as well. So in this equation, basically saying I'm solving for lambda 2 is a choice that I made. That's completely arbitrary. I could solve for lambda 1, and then I'd say lambda 2 is the free variable. The solution would be the negative of this, but the vector space that it spans is the same. Doesn't matter which I choose. Any multiple will do. Right? If you prefer that, you could also write pi minus pi pi. Yes? You would just apply Gaussian to this matrix here. Again, the problem here is that will give you the right results, assuming that the domain is not U, but instead R3. So for R3, this will all work fine. But the domain here is more restricted. So if you did that, you will then have to ask, given my result, what is the intersection of that with U? And that's what I really want. Right? And I avoid that by doing the computations only on U from the very first place. Should give you the same result, of course. Yeah, that's also a way to do it, and it's totally fine. But don't forget that intersection with U in the end, otherwise it's wrong. Sorry? I'd say this was one of the harder questions in this exam. Yeah, so a question like this, but without the U, but instead R3, that should be an easy question. With the U, that made it considerably harder. All right, let's move on, I'd say, to the next problem. Otherwise, you won't get a lot on that list done. The next is this one here, problem 6. Matrix representation. I don't think we did a lot of those yet, so about time we did that. Yeah, cover that one. Okay, so what do we have here? We have a coordinate system of R2. We have a linear mapping. And this is given through a matrix representation with respect to the canonical basis. I wouldn't have to mention that, by the way. If I just wrote, this is the matrix representing it, and didn't say anything about the coordinate system, just assume it's canonical coordinates. The task is to determine the matrix representation with respect to the basis B. Now, how do we do that? So what we have is FC. What we have is this basis B. What we want is FB. So we have to use some matrix transformations to get that, right? We have our FC. What this FB does, it represents the mapping F, and it takes an input in B coordinates, and you obtain an output in B coordinates. This matrix does pretty much the same thing, but the input and the output are in C coordinates. So if I want to use that to compute F for a B coordinate input, I first have to transform that input to C coordinates. So what I need to do here is I need to first apply a transformation matrix that takes B input and output C coordinates. Right? Remember, you always read that from the right because this is where the input is appended to that chain, right? So the input is in B coordinates. It is transformed to C. It is then processed by the mapping F. The output is again in C coordinates. We want that in B coordinates, so we'd have to transform it back from C to B. All right? So that's how those two matrices are related. And that means all we have to do is we have to compute these two transformation matrices here. Well, how do we get those? One of those is easy to get because we have B here. And that is the one that transforms B coordinates into C coordinates. Because that is simply given by the vectors in the bases as columns of the matrix. Right? What we do here is this TBC is minus 2, 2, 1, 1. Okay, that's because in B coordinates, the basis vectors of B themselves are 1, 0, and 0, 1. Right? The first basis vector is this one in C coordinates, and in B coordinates would just be 1 times this vector, 0 times this vector. So 1, 0. Now if I multiply this by 1, 0, I get this first column, and that's the C coordinates of that vector. So just what the transformation matrix should do. And same is true for the second column. If I multiply this by 0, 1, I get the second column. So this is the C coordinates of 0, 1 of that second vector in the basis. All right, so this one is for free. Now for the other one, the BC, what I have to do is I have to invert the matrix I already have. Okay, so this is a matrix inversion. You all remember how to do that, I hope. Let's do it the elementary way, just to practice it once again. Take the matrix, write the identity next to it, and then apply Gaussian elimination until this becomes an identity matrix, and the inverse is then on the right. Okay, so let's see. Let's start by adding the first row to the second one. So we copy row 1. The second row then becomes 0, 2, and 1, 1. Don't forget to also do these operations on the right-hand side. Otherwise, of course, your result will not be correct. Then, let's see. Next, we multiply this by 1 over 2 to get a 1 here. So again, we copy the first row. And the second one is 0, 1. 1 over 2, 1 over 2. Then we subtract the second row from the first one to get rid of this 1 entry here. So that will give us minus 1, 0. This time we can copy the second row. And the first one becomes, let's see, 1 over 2 and minus 1 over 2. And then finally we have to multiply this by minus 1 over 2 to transform this into a plus 1. So then we have the identity on the left. And let's see, we get minus 1 over 4 plus 1 over 4, 1 over 2, 1 over 2. And that looks about right. Okay, so that means our matrix is, let's take out the 1 over 4 maybe. Then we have minus 1, 1 and 2, 2. That should be it. Sorry? Where did I make a mistake? Well, which step? This one? No, sorry. This one? Where did I go wrong here? So I added. It's right? Okay, any other mistakes? Maybe let's just quickly verify just to be sure, because otherwise all the multiplications I do will be for nothing. So if I multiply these two, then of course I should get the identity matrix. So that's 1 over 4 minus 1, 1, 2, 2. And this other one was minus 2, 2, 1, 1, right? So let's see, that's 1 over 4. 2 plus 2, that's 4, that looks good. Minus 4 plus 4 is 0. Minus 1 plus 1, and 2 plus 2 is 4. That looks great, so that's I2. Okay, seems to be right. Good, so all that's left is do this computation and do it correctly. And that's probably the most challenging part here. So let's see. This first one is 1 over 4 minus 1, 2, 1, 2. Then we have FC. FC was given as 1, 5, 5, 1. And finally, this last one, this was minus 2, 2, 1, 1, right? And now we just do the multiplications. Remember, matrix multiplication is not commutative, so you can't just change the order of the matrices, but it is associative. So you can choose whether you first want to do this product or whether you first want to do this product. What you can't do is interchange the order of those two, for example. Don't do that. But otherwise, you're free to choose whichever order you might guess is nicer to do. Question? Could you speak up a little? Yeah. So to the first question, you can also compute this inverse matrix with the help of the determinant. We had a formula for that. Feel free to use that. That's basically useful for 2x2 matrices. There are formulas for higher dimension which we didn't cover, and I advise you not use them. They're just way too complicated. But for 2x2, that's totally fine. And you should get the very same result if you do that correctly. If you flip the sign somewhere, one of us is wrong. And you also had a question? Mm-hmm. So regarding this order of multiplication, the question is, how do these scalar factors here behave? What about this 1/4? And the answer is you can move that around as you want. It could be here, or at the very end, that doesn't matter. You can move around a scalar as you like. Yeah, and of course you can also take it into each of those matrices if you want to do that at any point. Okay, I usually like to keep them out until the very end to make things a little nicer, but that's just a matter of taste. All right, so maybe let's just start with those first two here. See what that gives us. So that's a -1 plus 5. That should be 4. Then I have 2 plus 10. That's 12. -5 plus 1. That's -4. And 10 plus 2. That's 12 again. Yep, I hope that's right. -2211. And now you can see the first matrix here, all of the entries can be divided by 4. So at that point, I just taken the 1/4 to make the rest a little nicer. So I get 1 minus 1, 3, 3. And let's see what we get here. This is -2 minus 2. This is -4. -6 plus 6 is 0. 1 minus 1 is 0. And 3 plus 3 is 6. So this should be the result, -4006. And of course, if you get a matrix that looks as nice as this is probably an indication that result is correct. It doesn't have to be that nice, though. Maybe I was just too lazy to get it nice. All right, I think that covers it, right? Was there anything else to answer? Nope. That should cover it. Any questions about this? Yes. What's the only thing I know about F? Right? So. Okay, so what we have here is this linear mapping, right? That's not bound to any coordinates per se. It's just a linear mapping. It could be something like rotate by 90 degrees. If I fix a coordinate system, I can represent that by a matrix, and that means I can write f in the way fx equals this representation times a vector, right? And of course, then everything has to be in the same coordinate system. So this matrix is with respect to C, and this is also a coordinate vector with respect to C, right? Okay, so now the question is, what I have in this problem statement is I have this f, and I know how it looks with respect to C coordinates. That's how it's defined, basically. Yeah, it's not given in any more abstract way, like rotate by 90 degrees. It's given in the way, well, if I have canonical coordinates, this is how its representation looks. So this is my definition of f. And now I'm saying I don't like canonical coordinates. I'd rather have these. How does it look in that system? Could you please transform it? And that's what I'm doing here. Right? So this is the definition, so to say, of my f. I could define it in other ways if you like that better. Good. Other questions? Yes. In the previous question, what was that? And what is the question? So you mean this one here? So my point here was, if the domain was R3 instead of this U, then I could use the, let's say, standard approach where I just take this matrix and then I'll say, well, the image is the span of the columns, so I just determine the basis for the column space, and the kernel is the solution of the homogeneous linear system of equations associated with that matrix, so I can solve that, and I'm done. You mean for what? For problem 6? There is no U here. Oh, so you mean if we had a U here? Oh, all right. That wouldn't make that much of a difference. In that case, of course, the coordinate system for the domain, at least, that would have to be one that works for that domain. So if, well, we are R2 here, say if we have just a line, not a whole of R2, but just a line as our domain, then we would need a coordinate system just for that line, right? So we would just have not two, we would have one vector in that coordinate system then. That could not work for the codomain if that was R2. We need two coordinates there, so we need different coordinate systems in that case. Otherwise, we could do pretty much the same things. Yeah? So it's not as restrictive, you just need different coordinate systems. Might even make things easier. Yes? How would I determine the first matrix if I didn't have that? This one here? Ah, so you're saying if this was not FC, but F, I don't know, D for some other D system that was also defined somewhere, how would I find that? Two parts to this answer. First, of course, these here are also vectors with respect to some coordinate system, right? It's not mentioned anywhere, so it's canonical coordinates. If those were also defined in terms of D, then it's the very same thing. If those are C coordinates and F is defined in terms of some third system, D, then things get a little more hairy. In that case, what I would do is I would transform it all back to C first. Right? So what I would do is I will come up with a transformation matrix of B to C and a transformation matrix of D to C, and then I could just combine those two. Right? So then, for example, I could get the transformation, let's say, from B to D. I could get that as DC times CB. And so I would have to invert this CD matrix and multiply with that. Yeah, so it's pretty much more of the same thing in a way. Yeah, you just have to come up with more matrices, invert more matrices, and then multiply them suitably to get the transformations that you actually want. Of course, there are also more direct ways to do that, but it's not really less work. You do the same things, you just do them implicitly. Okay, other questions about this? That does not seem to be the case. So what's next on the list? Let's see. We've covered matrix representation. So we have the next two are game theory questions. All right, two game theory questions. So it's either this one, or where was the other one? Or this one. Same number of votes. So let's put it to a quick vote. Which one would you like best? Which question? I'll just say 4 or 5. And come on. Nope. Once again, which question? If it doesn't work, we just do both. You want 4 or 5? Now it's working. All right, so as a vote and feedback, you're either one number 4, that is this one here, or number 5. Remember that here is number 5. Which one should I do first? I'll give you 20 more seconds. 10 more seconds. 1 more second. And that's the final result, so we'll start with number 5. All right, so this here is a matrix game given by this payoff matrix here. And the questions are to determine a Nash equilibrium and the value of the game. And second question, is that game fair? Any ideas of how to approach that? The matrix is Q-symmetric, correct, that's it. Okay, so have a look at the matrix. If you do that, you will see the diagonal is all zeros. The off-diagonal entries are just mirrored with a negative sign, right? 3 minus 3, 1 minus 1, minus 5, 5. So the matrix is skew-symmetric. And that makes this whole thing a lot easier. Right, so A is skew-symmetric. So the game is symmetric. And please remember the matrix has to be skew-symmetric for that, not symmetric. So this is important. And the game is still called symmetric. That might be somewhat confusing. Okay, so what does that mean? Well, yeah. Good. Sorry, could you come again? Uh-huh. Mm-hmm. Okay, so for a skew-symmetric matrix, as you correctly mentioned, we know the value is 0. Let me just write that down before I answer the rest of your question. Right, that means the value of the game is 0. And what that also means is the game is fair. It's just another word for the value is 0. The game is fair. So that would answer B already. Now, if we didn't have a skew-symmetric matrix, how would I get the value then? There's a couple of ways that I could use. Generally, what I need is a combination of optimal strategies. And the expected outcome in that combination is my value. So I somehow need to get optimal strategies. And basically, there's 2 ways of getting this, well, 2.5 maybe. The first is I could try and find a Nash equilibrium. In the Nash equilibrium, the strategies that I have are mutual best responses, so they're also optimal, right? None of the players would want to change. Unilaterally, that is. Or I could ask the question, well, given a strategy of one player, what would the other player do? How does he or she optimize her payoff? So basically, I'm solving these minimax problems. Minimax, maximin, I solve these two problems. I can also get a combination of optimal strategies that way. The general approach to do that is solve these problems via the linear programming formulations. That will always work. Sometimes if you just write down the expected value, you'll find an easier way of making this argument. Often using the fact that the strategies are non-negative, all strategies are negative, and they sum up to 1. And if you have just few strategies, it's often easy to see what the optimal choice has to be in some situation. Yeah? So one of these ways will hopefully give you a combination of optimal strategies, and then you just compute the expected outcome for that combination. That's your value. Okay? So much more complicated than this, unfortunately. Yes? That's what we're going to do now. That's what we're going to do now. Yeah, so let me just mention this one thing. So you all remember we solved a bunch of inequalities to figure out the optimal strategy. That's also something that works for a symmetric game only, right? So that's again a special case. Let me just write that down briefly. For optimal strategies, we need to find some x star with a x star is greater or equal to 0, right? For non-symmetric games, this is more complicated, but for symmetric games, this is the only condition we need. And then we have a pair of optimal strategies where both players do the same thing. And that works for any x star that fulfills these inequalities, or any feasible solution will do. For non-symmetric games, a pair of optimal inequalities can also have the same for both players, but it doesn't have to be that way. You could have different strategies for both players. Okay, so that's what we do for a symmetric game usually, because that's often the easiest approach. And I forgot the second part of your question. What was that again? Yeah. Oh, yeah. Yeah, so of course what you can also do in this situation is write down the inequalities, look at that hard, and then guess a solution. Yeah? You would, of course, have to prove that it actually is correct, but you can just do that by substituting it in that inequality and then seeing that it's all good. Yeah, please write that down. But otherwise, guessing is fine. Yeah, and that's true generally. If you can guess a solution, by all means do that. Just prove that it's correct. Right? So you can always say, I'm guessing this is the right solution. I substitute it in here, and I can see my guess was good. That's fine. If you have a magic intuition, that's great. And I need to come up with more complex numbers to avoid that. All right. So let's take a quick look at what happens here. If we write down a times x, a is this matrix here. I hope I copied that correctly. Minus 3, 5, 0. Is that right? Yeah, looks good. Times. So we have 3 columns. That means our strategy vector has 3 actions, 3 components. So what we get is, let's see, minus x2 minus 3x3, x1 plus 5x3, and 3x1 minus 5x2, And all of these have to be greater or equal to 0. And you remember what we usually did is we reformulated those slightly so that we only have one variable on each side, and then we tried to form a chain that started and ended in the same thing to turn this into inequalities and solve this system of equalities that we get. In this case, it's easier, although it looks harder. The problem that you'll find is this here. If you try to, well, also this here, if you try to reformulate that such that you have one variable on each side, one of those is always negative. That's not very nice. With this here, on the other hand, works out fine, right? So those three don't seem to be compatible in a certain way. But if you look at that more closely, take this inequality, for example. What you have here is minus x2 minus 3x3 is greater or equal to 0. We know x is a strategy vector, so in particular x is greater or equal to 0. Can't be negative. Right? So how can this inequality hold? Well, it does. But for what solution? If you multiply, okay, let's try that. If you multiply this by minus 1, what happens is the sign changes, that's right. But unfortunately also, don't forget to flip around the inequality sign. Okay, if that's easier. Exactly, yeah? So what you get from this is, well, this has to be less or equal to 0. How can that happen? Well, the only possible solution is this is 0 and this is 0. And that should be an x3, of course. Sorry about that. Right? So that means these two together implies that x2 and x3 must both be 0. There's no other way of fulfilling this inequality. Well, if x2 and x3 are going to be 0, and the sum of all entries is 1, well, that means x1 has to be 1, right? So the only possible solution is 1, 0, 0. And then, well, we've only looked at one inequality so far. We also have to make sure that it fulfills the other two inequalities. So let's compute a times 1, 0, 0. What we get is 0, 1, 3, and obviously that is greater or equal to 0. So that is a feasible solution. And that means 1, 0, 0 and 1, 0, 0 is a pair of optimal strategies, and a pair of optimal strategies is also a Nash equilibrium. So in fact, we even get a Nash equilibrium in pure strategies. And of course, you might also have argued that in a more elementary way. If you just look at the matrix and try to find an equilibrium in pure strategies and happen to find one, that's totally fine. Just need to make an argument of why this is a Nash equilibrium, but you could have seen that without those computations. All right, I think that covers it. Question? So I'm not quite sure if I got that correct. So you want to eliminate dominating strategies, dominated strategies first? So which one would you want to eliminate? The second column. That's right, yeah. So if you look at those two columns, let me just explain that briefly. You will find that the column player will always prefer the first column to the second column. So there's no way he's ever going to play column 2. He'll always play column 1 instead. So you could also eliminate that strategy first with this argument and then go on. Yeah, that's also fine. All right, we did cover everything, right? Yeah, any more questions about this one? Okay, so let's see, where were we then? This other game theory problem then, right? Number 4. Where did I have that? Somewhere back there? Here it is. I haven't written that one down. So, 2016 one. That's quite some time ago. Okay, now here's a game described in words for the row player and the column player. Each choose either the color green, first strategy, or the color blue, second strategy. If they choose the same color, the row player gets €1 from C, and otherwise C gets €1 from R. What is the payoff matrix? Well, let's see if we can get that right. So remember, the payoff matrix is always from the point of view of the column player. We have two strategies. They could choose green, that's the first strategy, or blue. So here we have green, that is the first row and the first column green, or blue. And then what is the payoff? Well, if they choose the same color, the row player gets €1. So C pays €1, right? So from the point of view of C, the payoff is -1 for the same color. So green, green, and also blue, blue. And otherwise, C gets €1 from R. So from the point of view of C, the payoff is +1 in those situations. So here's a +1 here and a +1 here. Right? So that would be the payoff matrix of that game. Right? And then B, what is the value of that game? Well, in that case, if you look at that matrix, this is not skew symmetric, so it's not as easy as that. Value might not be 0. It might still be 0, by the way, right? We also have non-symmetric games that have a value of 0. So in this case, we need to find an optimal strategy. One possibility here would be to just try a guess. And the game looks simple enough, so I would try to wager a guess here. Sorry? The value is 0? How do you know? Mm-hmm. It's symmetric, but it's not skew symmetric. So the matrix is not skew symmetric. That means the game is not symmetric. Don't confuse those two, right? But I guess you were right about the first part. So you say they have equal probabilities. More precisely, I think what you're saying is suggests you play a strategy of 50-50, right? I choose each of those my actions with a probability of 1/2. That should be an optimal strategy. So we can try that. Just let's guess that. Right, so my guess is y equals 1/2, 1/2, and x equals 1/2, 1/2 is an optimal pair of strategies. How do we prove that? What we have to do is we have to fix one of those strategies and then ask what is the other player's best response to that. And if the answer is 1/2, 1/2, in both cases, then we're right. Okay, so let's say fix y to 1/2, 1/2. Let's say the row player chooses this strategy, then the payoff is 1/2, 1/2 transposed times A. A is this matrix here, times And then we have x1, x2 for the column player. So if we do those computations, we'll see that we just get 0, 0 times x1, x2, right? So the expected payoff is 0, no matter what the column player does. So every strategy of C is the best response to y equals 1/2, 1/2, right? In particular, the one that we claim is this x equals 1/2, 1/2. So that is a best response. Not the only possible best response, but it is one. So that was the first part. And then the other part is just the other way around. We now fix the column player strategy, x at 1/2, 1/2, and ask the same questions. The payoff is then, and now for an arbitrary strategy of the row player. So now the question is, what is row's best possible answer? What optimizes his payoff? And of course for row, optimizing means minimizing. So again, we compute that. And again, we get, well, this is y1, y2 times 0, 0. And this is 0. And again, that means every possible strategy of the row player is a best response. In particular, this one is. Is the best response to this strategy of the column player. Right? So that means those two strategies are mutual best responses. No one wants to change in that situation. And that means we have a Nash equilibrium. So 1/2, 1/2, and 1/2, 1/2 is a Nash equilibrium. And thus also a pair of optimal strategies. And thus the value is the expected payoff in that situation. And we have already computed that, so the value is 0. Yeah, so you were right about the value. Yeah, but what would that have to do with an optimal strategy? So what you didn't use in your argument is the actual payoffs, right? I could change that thing. I could say, well, let's make it -5, 1, 7, -9, like this. You still think your argument is valid for that payoff matrix? It doesn't change the setup. Everything that you used in your argument is still the same. But I'd say that might change the optimal strategies. Yeah? So my guess is that makes the game a little unfair in favor of probably the row player. I didn't compute that yet, but if you try that, I guess you get a different outcome. So no, that doesn't work generally. Yes? No. Nope, I didn't make the computations again, but probably not. So what you're saying is fix one at 1/2, 1/2, and the other at, let's say, 1/3, 2/3, something different. Because what we said is if you fix this at 1/2, 1/2, then all strategies are a best response. Yeah. So this still is valid. What might not work is the other way around. We also need that. So in that case, we'd have to say, well, fix this to 1/3, 2/3, and then figure out if 1/2 was still the best response. If that's true, then yeah, you're right. My guess is this will not be true anymore. Yeah, so you need both arguments, both sides of the argument, otherwise it's not complete. The determinant is what, sorry? The determinant is the value, why would that be? I don't think it works in general. If A is symmetric, I don't think so. So I tried to find a counterexample. Forget about that. Yeah, question. Maybe I don't get the question. So you're saying is, can we compute the value by computing the payoff in optimal strategies? And that's exactly what we did. So you're trying to leave out one of those two steps. How do you know it's a pair of optimal strategies then? You don't know the value. If you know the value before, then of course you can use that. Yeah, then you're right. Any combination that will achieve that value is necessarily optimal, right? You can't. So if I fix one strategy and then for the other player to be optimal, I just need to achieve the value that I already know. You can use that argument, of course. Yeah, that's fine. But for that, you have to know the value beforehand. And in that case, I wouldn't know that beforehand. This was not a skew-symmetric matrix. The other one was. Let me just get back to that matrix. So this here was a matrix that's not skew-symmetric. Yeah. Yes. Mm-hmm. So let's say you might not be able to take a good guess here. How could you still come up with the right solution? So what you could do in this case is set up the linear programming problem. You remember how those work? You only have two variables here, and that makes it a little easier, right? So you have x1, you have x2, and then you would also use x1 plus x2 equals 1. And basically you could use that to replace, let's say, x1 by 1 minus x2 by 1 minus x1. So then you're left with an LP in just one variable, and it should be feasible to see the optimal solution in such an easy LP, right? So that way you should get the optimal solution. And if you still can't see it, you'll be forced to do a simplex algorithm, but that shouldn't be too much work in that situation. But I guess it's not necessary. Yeah, but generally, if you don't see a solution, set up the LP and see if that helps. Yes. Yeah, so in the exam, you'll have, I think it's 4 extra pages at the end of the exam booklet that you can just use for any notes, calculations, anything you want, and also as extra space if you need more space somewhere. Yeah, that should be sufficient, I hope. If it's not, we'll also have extra paper, but just scratch paper. We will not collect any of that extra paper. All right. Somewhat surprisingly, even if I do all the work myself, I'm not getting a lot further. All right, so that covers the 2 game theory questions. And that means we have, I think, 4 of them, right? Serious. Maybe let's have a quick look at the serious before the end. Where is that problem? was 8, right? Do I have that anywhere? Here. All right, that one should be quick. I think that was the next one on the list, if I'm not mistaken. Yes. Good. So first question, does that series converge? Or so maybe let's first read both of those questions. In the first question, it asks, does that series converge or diverge? Give a justification. If you read carefully, you'll notice the second question says, does it converge or diverge? Determine the limit. If applicable, I shouldn't use that word. So that should already give you a hint that for the first question, we're not asking for a limit. So either this thing diverges or it's something that you can settle by something like root test, ratio test, things like that, that don't give you a limit. So that's what I would try first. And in that case, you'll also notice there's a factorial in there. Yeah? That should also give you a good hint that maybe the ratio test is a good first try. So I do that. Ratio test with, well, our an is then 2n squared plus 1 over n factorial. And remember, ratio test, I have to take this ratio, absolute values. It's all positive here, so I don't need the absolute values. And what I get is 2n plus 1 squared plus 1 over n plus 1 factorial times, and 1 over an is n factorial over 2n squared plus 1. The factorial can almost be eliminated, so what I'm left with is 2n plus 1 squared plus 1 here. There's an n plus 1 left over from that factorial. And then I have 2n squared plus 1. Right, and now this is a fraction of polynomials, so I can just divide by the highest power of n. Here I have an n squared. Here I have an n squared times n, so n to the third. So the highest power is n to the third. That means I get something like, let's see, 2 over n. Let's have one n out here, and I'll take the other one in the square here. So this is 1 plus 1 over n squared plus 1 over n to the third. And in the denominator, I get 1 plus 1 over n, 2 plus 1 over n squared. And now if n goes to infinity, this here, the denominator goes to 1 times 2, and this here goes to 0 plus 0. So it all goes to 0. Obviously, this is less than 1, so that means the series converges. All right, questions? No questions, great. Then let's do the second one quickly. So again, in this case, I'm asking for the limit, and that should be a hint that the limit might actually exist. And maybe root test or ratio test will not be the first thing you should consider. And if you look at that, you should hopefully discover that has a close resemblance to the geometric series. So I would try to reformulate that as a geometric series. First thing we need to make sure is that we have the same values here and here, right? And we can easily achieve that by factoring out 1 over 5 squared. And then we get 3 to the power of n minus 2. I didn't touch that one. And then 5 to the power of n minus 2, right? I took out 2 and added them here. And I'm almost done. This is 1 over 5 squared. Sum from 2 to infinity. 3 over 5 to the power of n minus 2. So almost the geometric series. Actually, if you look closer, you see this is exactly the geometric series. Because what happens here is I have an n minus 2 and I'm starting from 2, right? So the first exponent here is 0. The next is 1. Then it's 2, 3, 4, 5, and so on. So I could just rewrite that as starting from 0. And then I just write to the power of n instead of n minus 2. Right? Very same thing. So this is exactly the geometric series. Oh, no, I forgot a square, by the way. Sorry. 1 over 5 squared. And we know the limit for the geometric series. This here is less than 1, so this converges. And it converges to 1 over 1 minus this expression, 3 over 5. So we get 1 over 5 squared times 1 over 2 over 5. So that is 5 over 2 times 1 over 5 squared. Or reducing a 5, we get 1 over 10. So this does converge, and the limit is 1 over 10. Question? You mean this one here? So basically what I did is I rewrote this expression here as 5 to the n minus 2 plus 2, right? And that is 5 to the n minus 2 times 5 squared. And then I took out that 5 squared. You could also do that differently. You could also say what I could take this here instead, right? And I could say, well, this is the same thing as 3 to the power of n. And then I'd have to divide by 3 squared. And you could take that out. Should get you the same result. Other questions? Right, yeah. Yeah. It can be, so the question is, I wrote down that this someone here, this here has to be less than 1, and the question is, can it be negative? The answer is yes, that's possible. As long as the absolute value is less than 1, this will converge. Right, so minus 3 over 5 would still converge, and the same formula would work. Minus 5 over 3 would not converge. Yes? Sorry? Do I have to factorize out 1 over 5 squared? Well, I'm doing that to get the same value in this and this exponent, so that I can then rewrite it in this way. That's the reason for doing that. And that's where it lands. Right? I'm taking it out of the sum. I could have left it in the sum first and then taken it out later, but just to make it easier. How would I get rid of what? If I choose, so if I take out the 3 over 2, I wouldn't get, so I would also take it out of the sum. And in the end, then multiply it with whatever result I get, and no need to get rid of it. Give it a try. You see that works smoothly. All right, so before we start exercise class, I still have a couple of words I'd like to say. And this is the last chance to do that. So maybe give me 5 more minutes if that's okay. Just a second. All right, first of all, I haven't talked about the evaluation yet. I'm not going to spend a lot of time doing that now. I think it's going to be published anyway, so I hope you will get a chance to look at that. Here's a few selected, very few selected comments from the evaluation that I just like to present. One thing that I tried this year with this course is this flipped classroom approach, where you get the videos beforehand. I expect you to watch them, and then we briefly go over the contents and do a lot of additional example problems. And for me, that was a positive aspect. I got to do a lot more practice and examples than in other years. However, what most of you also noticed is that this was actually a lot of work. My argument about that would be the work that you have to put in is pretty much the same as with traditional approaches, but now it's more obvious, right? Usually, you go to class, I'll present the new topics, you probably wouldn't get much of that, and then at home you'd sit down again, maybe watch the video recordings of class, maybe go through your notes again, maybe try to come up with a few examples yourself so that you actually understand those topics. So you'd have to spend pretty much the same amount of time after class instead of before class. And now, of course, by presenting you those videos and then assuming you had watched them, this effect became pretty obvious pretty quickly. That would be my take on that. I might be wrong, however. As I said, I've tried this the first time. I've gotten a lot of feedback from the evaluation. I would still be very much interested in talking to a few people. So if you want to give me your feedback, I'd be very interested in sitting down with you and going over the feedback. I think you're the semester speaker, right? So I would be very happy if we could take some time out of your busy schedule. Maybe sometime after the exams. I guess you have better things now. Just great. So maybe we can try and schedule a meeting later on. Wonderful. There is more rude comments in there that I'm not presenting here. But again, I'll be happy to go over that with you if you have some time. And of course, anyone else who'd like to contribute is also invited, especially the ones who agree with those comments. I'm very interested in your feedback on that. So if there's anyone who agrees with that, I'd be happy to meet. This is a positive comment. There's also been positive comments. And this is one of the comments I'd like to specifically address. Apparently, my course stands out in terms of its high failure rates. That was back in December, I think, far from the exam that you didn't even write yet, so no failure rates. I've also heard rumors that we have failure rates of 70% and higher in this course, in my course specifically. So I looked at some statistics, and maybe that helps. So this was not my course, to be honest. But if you look at the statistics here, you can see there's a failure rate of slightly above 20%. That is pretty good, I will admit that. There's also a lot of very good marks here. That's not the case all the time. So here's one that looks a little slightly worse. 21.7% failure rate. Again, quite a few good marks still. I think someone asked last week if it's possible to get a 1.0 in this course. It is. Here's 2020. That was not that good. We had 38%, and I'd say that was one of the worst years. But still, very good grades are possible, and we're far away from 70%. And if you go, well, I did that until 2018, I think, no, 2017. So again, that's one that stands out for a pretty high failure rate, I'll admit that, but still, way below 40%. And just to reiterate that, my goal is not to make you fail this course. So I'm not aiming at a high failure rate at all. I don't have anything to gain from that. To the contrary, if I have a high failure rate in my first exam, that means all of you will come back to the second exam and I'll have to correct all of you again. I'm not interested in that. All right, so hopefully that helps to dispel that rumor that failure rates are 70% and higher. My expectation would be hopefully something around 30%, maybe less, maybe a little more, I don't know. But in my experience, that's a failure rate that is normal for a course of this size, in a way. Yeah, but be very far away from 70%. Two more things I'd like to quickly mention. You might remember these slides here. I presented those at the beginning of this semester, and if you look at those again, it's a very quick overview of all the topics that we have discussed. You can see that this was a lot of things to process, and I'm well aware of that. It was also something that was mentioned very often. We do have to discuss lots and lots of topics in this course. So the pace is pretty challenging. That is true. I just didn't find a good way of, let's say, making the pace slower and still teaching you all these things that you apparently need to know. Let's just say it wasn't my decision to put all of this in this course. If you look at the module description of that course, you'll even notice that I moved some of the topics to Math 2 to make it a little easier here. That's calculus, just to complete that. So also lots of topics in calculus that we discussed. So what I want to say with that is basically, you learned a lot in this course. At least I hope you did. You should have learned a lot in this course. And I think you can be proud of yourselves. And for those who are still not satisfied with that level of knowledge, here's a quick preview of what we're going to talk about next semester if you're still interested. Basically, the topics in that next semester will all evolve around multivariate calculus, so calculus in higher dimensions. First topic that we discuss is somewhat of a bridge between those two worlds. We're going to discuss differential equations, so equations that relate functions and their derivatives. Those turn up in pretty much all engineering applications, in physics, all over economics. That's all differential equations. And we'll discuss some techniques and some methods for solving systems of these equations. Specifically, we'll introduce what is known as eigenvalues and eigenvectors. I'm not going into detail about those now. We talk about complex numbers, and we talk about diagonalization. We've already seen a few hints of those. Basically, the question of diagonalization is, if I have a linear mapping, how do I find a basis where that mapping looks nice? What is the natural basis for that mapping in a certain way? So that's kind of a bridge between linear algebra and calculus in higher dimensions, and then we'll focus on multivariate functions. We learn how to differentiate in higher dimensions. We learn about vector-valued functions, so functions that have more than one input parameter and also more than one output. We talk about coordinate systems for those functions. Specifically, we'll discuss polar coordinates, cylindrical coordinates, spherical coordinates. We'll discuss the use cases, of course. The idea basically is, again, what we want to do with these functions is we want to optimize. So we want to find maxima and minima of those functions. And we'll learn the tools necessary for doing that. Amongst those tools is, again, Taylor approximation. There's an analog of that in higher dimensions. We talk about optimization with and without constraints. We'll also talk about numerical methods for doing that in case the analytical methods fail. And then in the last part, we'll again talk about integration, this time again in higher dimensions. So instead of just integrating along the line, we'll discuss volume integrals. Basically, that means integrating about higher dimensional spaces, like with the domains R2, R3, or something like that. We talk about parameterized curves, so that means modeling curves through space, something like that here. That's a parameterized curve. And of course, you can integrate along curves as well. We'll do that. And then we'll discuss vector fields. Vector fields are basically useful for modeling forces in some space. So for example, wind, right? Wind has a direction and a force, so that can be modeled as a vector field. And of course, again, we'll be interested in how functions behave in vector fields and how we can integrate over vector fields to get information about this behavior. Of course, there'll also be lots of applications, again, both in economics and in engineering, that we'll have a look at for all of these issues, for all these methods here. right? So basically, higher dimensional calculus is the main topic of Math 2. Again, if you're interested, I'd be very happy to see you again. So I'll see you on Monday for the exam, and hopefully I'll see you in summer for Math 2. And of course, good luck for the exam.